Hello, my name is Matteo Sonza Reorda. I'm a professor at Politecnico Torino in Italy, and my research area focuses on integrated circuit testing. I have a special relationship with the European Test Symposium. I attended practically all editions. I was the program chair of last year edition, so I was particularly happy and honored when the organizers of the European Test Symposium asked me to prepare and deliver this short talk introducing the main concepts about the integrated circuit testing. What we will see today is first of all a brief introduction about the key concepts and the vocabulary that is used in this area. Then we will focus a little bit on the stack-at-fault model, being the most popular one, at least for digital circuit testing, and we will show how it is used, which are the benefits stemming from the adoption of a fault model in the whole test generation process. We will then widen a little bit the view and speak more in general about the test generation process, what is done practically in order to perform the test and prepare the test. Design for testability and in-field test are crucial topics today, and I will spend a few minutes introducing them during the talk. And I will finally draw some conclusions. Well, let's start from the introduction. And first of all, it is crucial to define exactly what a test is. Test is the process aiming at identifying defective products. So there is a production line, in this case, manufacturing integrated circuits. And at the end of this line, no matter how good the manufacturing is, there is the possibility that some of the products are faulty, includes some defects. So the primary goal of testing is to distinguish between good products and defective products, so that defective products can be typically thrown away and do not reach the customer that will then use them for mounting them on a PCB, in a system, and so on. So the output of a test is binary. Either the specific integrated circuit is placed in the bin of good products that will go to the customer, or it will go into the bin of defective products that will probably be discarded. Now, a few important notes about integrated circuit testing. The goal here, the one we will deal with during this brief talk, is simply to identify defective products from the point of view of products having hardware defects. So the goal here is not to check whether there has been any bug in the specification or in the design of the hardware or wherever else. Here we are not speaking about bugs, we are speaking about defects affecting the hardware. And we will basically speak mainly about defects coming from the manufacturing due to some issue during the manufacturing. We will also add some information and ideas about defects that may appear during the operational phase. Once again, for the purpose of today's mini course, we will only consider defects affecting the hardware of an integrated circuit. As I said, the main focus here is on end of manufacturing test, the test which is done by semiconductor companies at the end of the manufacturing process, leading to the delivery of integrated circuit. Now, one key point here is remember that all integrated circuits are tested after production. So test is not done on a sample base, on a statistical base. It is done on all products. Why? Because no matter how detailed and tuned and well organized the manufacturing process is, given the complexity of today integrated circuits, there is always a non-negligible possibility that some defects exist inside. So it is always the case that integrated circuits are tested one by one at the end of the production. Unfortunately, given the complexity of integrated circuits today, including billions of transistors, up to billions of transistors, their test may be extremely complex. So it is not like testing a resistor in which you apply a voltage and you measure a current and everything is done. Here you need to check whether every transistor inside the circuit works correctly, every connection has been manufactured correctly, and so on. You need to test everything. For this reason, for this complexity, the cost for test today may represent a significant component with respect to the overall cost for IC production. In the past, the technology was ensuring that a circuit which passed the test at the end of the manufacturing, so a fault-free circuit, was expected to operate correctly for a long period, 5 years, 10 years, 20 years, even more. Unfortunately, this is not true anymore today because the new semiconductor technologies are not able to guarantee such a long operational life. This means that there is a non-negligible probability that even an originally fault-free circuit will continue working for a sufficiently long period. Defects may arise even during the operational phase, and when the circuit is used in one of the so-called safety critical domains, think about healthcare, automotive, space, just to mention a few, it is crucial to check continuously whether any defect appeared in it, which may impair the correct behavior of the circuit. So this kind of test, which is performed while the circuit is already in the operational phase, while the circuit is already mounted on a board which operates inside a system, it is called in-field test. We will speak a little bit more about in-field test at the end of the talk, while we will now go back to focus on the end of manufacturing test. We introduced a test having a binary outcome, either good or faulty. Another key concept is diagnosis. When we discover that a circuit is faulty, in some cases we also need to understand which is the defect responsible for this faulty behavior. So we need to understand what is wrong inside the circuit, and this may be this interest may be due to mainly two reasons. First of all, during the first phase, in the let's say life of a product, you may need, the semiconductor company may need to optimize the manufacturing process, removing those, let's say, parameters, or improving those parameters that may lead to some faulty devices. So it's a matter of understanding what is wrong so that we can improve the manufacturing process, so that the manufacturing process increases the outcoming yield. Okay? We need to understand which defects are inside for this reason. Second reason, there are a few cases, in particular in the area of memories, where if you know which is the defect inside the circuit, you can fix the circuit, repair it by reconfiguring it in some cases. Okay, once again, you need to know exactly what is wrong, which is the defect existing in the circuit. In this case, we speak about diagnosis. So while test only aims at distinguishing between good and faulty circuits, diagnosis works on faulty circuits and aim at identifying the defect responsible for a given misbehavior, a given behavior different than the expected one. Diagnosis is more complex, it requires more effort, more time, and it is done only when strictly required. When speaking about defects that may affect an integrated circuit, it is crucial to distinguish between permanent defects and temporary defects. Temporary defects are those that appear at a given time but then immediately disappear. A typical example is a bit flip. Due to different reasons, for example, radiation effects, the bit stored in a memory element or in a flip-flop may be flipped. Okay, this is a temporary defect. It affects the circuit, which does not work correctly, but the circuit structure is typically not affected, and the circuit, if reset, for example, may continue working without issues. On the other side, there are permanent defects. Something that starts at a given time, either during the operation phase or during the manufacturing, and from that time on, this circuit structure will stop working correctly. Okay, this is a permanent defect. And for the purpose of this talk today, we will only focus on permanent defects. Now, a key concept. If you consider an integrated circuit, and especially a complex integrated circuit produced today, the list of possible defects that may affect it is practically endless due to its complexity, due to the complexity of the semiconductor technology which is used to manufacture it. So from a test point of view, in principle, the idea could be, yes, let's list all possible defects, let's check whether any of these possible defects exist, and only if no one exists, I can label my circuit as good, fault-free. Now, this approach is unfeasible with today's circuit because they are too complex, as I was saying. So we need a more practical approach. And the practical approach is based on introducing what are called fault models. A fault model is a representation of possible defects, which is hopefully easier to manage, so that we can more easily generate the test stimuli which are used during test, and we can more effectively perform the test. The most commonly used fault model by far is the stacked fault model, at least for digital circuits. This is the reason why we selected this fault model, and we will focus on this fault model only during today's talk. Still some vocabulary which is important. Until now we spoke about defects. Defects are, let's say, the bad things happening that may happen in a real circuit, changing its structure and hence its behavior. We just mentioned that the defects are very numerous, very complex to deal with. So very often we deal with faults and fault models. So faults are easier to manage representations of defects. Faults are inside the circuit, so they are not visible from the outside. So we can hardly understand when a circuit includes a fault if because we cannot access the internal part of the circuit. However, when a fault exists within a circuit, if the let's say stimuli are suitable, this fault may evolve into an error, meaning that we can move from a circuit structure not working correctly to something wrong happening in the circuit. For example, the value produced by a gate is different than the expected one. The value, the bit stored in a flip-flop is different than the expected one. The bit stored in a memory cell is different than the expected one. All these effects of a fault are called errors. Errors, once more, are not visible from the outside, but they represent a difference existing inside the circuit, so that some, let's say, visible effects, if I can look inside, is already there. Finally, errors produced by faults may evolve into failures. A failure is the effect of a fault affecting the outputs of the circuit. In this case, since the failures affect at least one output of the circuit, I can see them from the outside, so I can detect them. In general, we need, first of all, to distinguish between faults and errors inside the circuit and failures, which are the consequences on the circuit outputs. And it is crucial to underline that what we do when implementing a test is basically observing failures produced by faults. So the basic scheme of test, which is the one reported here, is based on taking the circuit under test, applying to it some test stimuli, which are not typically random stimuli, which are very suitably and carefully produced stimuli. We will apply them to the circuit under test. We will gather the observed system response, and we will compare it with the expected system response, the fault-free one. If there is a mismatch, it means that a fault exists inside the circuit under test. If not, it may be that no fault exists, or it also may be that the test stimuli are not good enough in exciting the fault and making it producing a failure. But the key concept is that we will observe failures produced by any generic fault when some test stimuli are applied to our circuit. Now we can introduce two crucial test phases during the whole test process. There is a preliminary test phase, which is the test generation, which is done before the circuit is manufactured. And then there is, this test phase, test generation phase, aims at generating the test stimuli to be applied during the test. Then there is a test application phase in which the real circuit has been already manufactured and it is stimulated with the stimuli generated in the first phase. So to, let's say, clearly identify the two phases. The test generation phase is typically performed before manufacturing, acting on the circuit model, which represents typically in a very accurate manner the circuit which will be manufactured. Using this model, we will be able to generate a list of faults and to generate a proper stimuli able to detect all or most of them when applied to the circuit under test. During the test application phase, which happens later when the circuit has been manufactured, so a given time later, what we will do is to, let's say, use the test stimuli generated during the previous phase, applying them to the inputs of the circuit under test, observing the produced outputs and comparing the results with respect to the expected ones. Then, according to the result of this comparison, if there is a mismatch, the circuit will be labeled as faulty and put in a different bin, or it will be labeled as good and it will be typically delivered to the customer. During this phase, a key role is played by the tester. The tester, or as it is more technically called, the automatic test equipment, or ATE, is the equipment, the system which is used to pick every circuit under test, to place it on a specific head, a station where we can easily apply the stimuli, observe the outputs, and the tester is clearly in charge also of comparing the observed outputs with the expected ones and checking whether they match. So, to summarize, the ATE should apply the stimuli, sample the output values produced by the circuit under test, and compare the sampled and the expected values. In order to do so, the ATE should be able to manage a relatively large amount of data to be applied to the circuit, to be sampled by from the circuit outputs, and to compare these sampled outputs with the expected ones. And this operation should be done at a high speed, in some cases at the operational speed of the circuit. So imagine when you want to test a high-speed circuit, you need some ATE running at least at that speed or even higher, because the comparison must be done very quickly. Now, this is the reason why ATE are very expensive, or may be very expensive equipment, costing up to millions of US dollars. Now we can move to the stacked full model, using it as an example of what a full model is and how it is used in practice. I introduced already the idea that it is not viable to deal with all possible defects inside an integrated circuit. They are too many and they are too complex. For these reasons, we typically don't use and don't consider defects, but we deal and we act on logical faults, which are called fault models. So basically the idea is, based on the characteristics of the technology, based on the experience coming from the possible defect that may appear in that technology and in that manufacturing process, someone introduces some fault model. And the fault model is a representation of the possible defects, easier to deal with, easier to manage, and allowing the test to become simpler and more effective. The most commonly adopted fault model for digital circuits is the stacked fault model that we will consider now. What is the stacked fault model? It is relatively simple. The idea is to say, okay, let's consider the gate level netlist, the gate level representation of our circuit. For every line, what we can assume is that it can be affected by several possible defects, but these defects will manifest themselves in two possible manners. Either the line will be permanently stacked at the zero logical value, or it will be permanently stacked at the 1 logical value. And this will be repeated for every line. So if the circuit is composed of n lines, there will be 2n possible fault models. And we will consider these 2 times n possible faults for our test purposes. Let's consider a simple example, a very simple combinational circuit. What we can imagine and consider here is a specific line. Let's consider in particular line D. And let's imagine that this line is affected by a fault corresponding to this line being stacked at 1. So it is permanently forced to the value 1 by some defect. Okay? No matter the value I will apply from the outside to the line itself. In this case, it is an input line, but it is just an example. Clearly, if I want to detect the possible occurrence of this fault, line D stack at 1, what I need is first to create an error inside the circuit due to this fault, created by this fault, and then to propagate this error so that it becomes a failure, which in this case can only be visible on output U, since there is a single output U. Clearly, if I apply this input stimuli 0011, this input pattern, to the inputs of the circuit, well, the line will be forced to 1 and I will not excite the defect, the fault. In order to excite the fault, I need to force on D the value 0. In this case, I will create an error on line D, because in the good circuit there will be a value 0, and in the faulty circuit a value 1. Now the problem is that I wanted to propagate, to make this error visible, propagating it up to the output U. Using this vector, this is not feasible. Why? It is not feasible because the gate, the lower end gate, which I'm highlighting, has the other input forced to 0, and hence its output, G2, is forced to 0 in any case. It does not depend on the value on D. Okay, so 0010 is not a test vector for my fault. If I move C to the value 0, the lower end gate has a 1 on the other input with respect to D, and the effect of the fault is propagated to its output. The same happens with the final OR. If I want this difference, this error, to propagate to U, I need the other input of the OR to hold a transparent value. And in this case, with the OR, the transparent value is 0. So I need to have a 0 on G1, which can be obtained, for example, forcing A and B both to 0. Okay? In this case, the error appears even on U, and it becomes a failure, because it is a difference on a visible output of the circuit. To summarize, using this input vector 0000, the fault is both excited and propagated. Hence, this input pattern represents a test pattern for our fault. Once again, this means that I need to force the input values, take into account of the need for exciting the fault, forcing the fault location to a value which is the opposite of the one forced by the stackette, and then propagating this difference, the difference that I created in the fault location, up to at least one output. And this is the propagation or observation part. Okay, so in our case, there was a single constraint for exciting the fault, D equal to 0, while in order to propagate the fault effects, I needed to force the other input of the AND to 1 and the other input of the OR to 0. And these are, if you want to call them as such, the propagating conditions for testing our fault. An important observation is that at this point we understood that the vector 0000 is a test vector for our fault. However, it is not the only vector, because other input patterns like 1000 and 0100 also let's say match the propagating conditions and the excitation conditions, which means that this fault can be detected by three vectors which build or constitute the test set for our fault. Until now, we considered the fault model, and we assumed that a single fault exists in our circuit. For every line in the circuit, there can be two possible faults, the stack at 0 and the stack at 1. And the common practice is to only consider single stacked faults in a circuit. Why? Typically because the probability of having a multiple stacked fault in a circuit is negligible. And because dealing with multiple faults is also quite tricky. So the number of possible multiple faults in a circuit composed of n lines is huge, 3 to n minus 1, very large. The number of single permanent stacked faults in a circuit composed of n lines is much more reduced, is 2n. It grows linearly with the size of the circuit, and this is another nice feature of the stacked fault model, which is also one of the reasons why it is so popularly adopted. The number of stacked faults in a circuit hence depends on the number of lines. Let's consider a simple example, the same circuit as before. Which are the fault locations? There are, in this case, 8 fault locations, 8 lines where a stacked may exist. This means that there are 16 possible stacked faults in our circuit. The circuit which we were using to provide example of usage of the stacked fault model was a simple tree circuit. And clearly in real circuits it is common to have fan-out branches. Now with fan-out branches the situation is a little bit different because we need to consider both the faults on the stem line and the faults on the branch lines. And we need to consider all of them because they can be tested by different sets of test vectors. In particular, you can easily understand that if you consider a fault on this stem line, well, you will need to excite this fault. And the conditions for exciting this fault are the same as the conditions for exciting the corresponding fault on any of the branch lines. However, the conditions for propagating a fault on the stem are different than those for propagating the faults on the branches. Why? Because for the stem, there are, in this case, 2 possible paths going towards the output. On the other side, on the 2 branch lines, you only have 1 stem. So to summarize, for faults on the branch lines, you typically have a different number of possible paths the fault can propagate through up to the outputs. While for the faults on the fan-out stem, the number of possible paths is higher. The result is that the faults on a fan-out stem are not detected by the same set of input values with respect to the faults on the fan-out branches, and the corresponding faults should then be all considered without neglecting any of them. In this case, in this specific case, this means that we should consider 3 possible lines and 6 possible faults. Let's come to a further example. Let's consider this circuit with a fan-out branch. In this case, let's compute how many stacked faults we should consider. Well, let's start with the fault locations. They are marked here. As you can see, there are 8 possible fault locations, providing up to 16 possible faults. Still speaking about fan-out branches, A specific case, which is a common one, is the one of reconvergent fanouts. Reconvergent fanouts are a problem when generating test vectors for stacked faults, because a specific phenomenon called masking may arise. Let's see a simple example, and let's consider a stacked one on this central line, input line for this circuit. And let's imagine we want to generate a test vector for the stacked one on this line. Now, in this case, I have different possibilities. Clearly, the easy starting point is to excite the fault, meaning that this input line should be forced to 0. And in this way, I will create an error on the fault location. Now I need to propagate this error. And the propagation may happen in different ways. Let's assume that we want to propagate this error through both the upper path and the lower path. For this purpose, it is enough to place a 1 on the upper input line and a 1 on the lower input line. This allows the error to propagate through the upper path, so a 0 in the good circuit and a 1 in the faulty one will appear on the upper inputs of the final end, and through the lower path, and in this case a 1 will appear on the lower input of the final end in the good circuit and a 0 in the faulty circuit. Unfortunately, this means that in the good and faulty circuits, the combinations of inputs for the final end will force the circuit, the fault effect to disappear, because the 0 and 1 in the good circuit will produce a 0, but the 1 and the 0 in the faulty circuit will also produce a 0. So the fault effect, the error, will disappear on the output. This is called masking. So the fault effects do propagate through different paths. The number of inversion on the different paths is different, is 0 on the upper path, 1 on the lower path, and the result is that the fault effects do mask each other in this case. The final result is that the input vector 1, 0, 1 is not a test vector, because no error, no failure is generated on the single output of this circuit. Clearly, in this case, the problem can be easily solved. I could simply use the upper path, leaving this 1 on the upper input, and let's say blocking the propagation of the error through the lower path by forcing a 0 on the lower, on the lowest, let's say, input signal. In this case, there is no reconvergence of the fault effects, and the fault can be easily detected on the output. So 1, 0, 0 is a test vector for the fault we were considering. An interesting phenomenon is the one corresponding to untestable faults. What is an untestable fault? It is a fault for which there is no test vector. How can this happen? How can this happen? Well, let's see an example. This is a relatively more complex circuit, and let's consider a fault where H is stacked 1. First of all, let's consider what we need in order to excite the fault H stacked 1 in this case. Clearly, I need to force a 0 on H. And in order to force a 0 on H, what I need is to force both D and E to 0. Otherwise, the OR will never produce the 0, okay, on its output. This means that going to E, this is a NAND gate. This means that both B and C should be forced to 1. Otherwise, E will not be 0 and H will not be 0, as expected, as required. Now, if B and C are forced to 1 in order to have E equal to 0, it means that in order to have D equal to 0, A should be 0. Now, this means that we practically forced all inputs to a specific value, this one. Okay, so in order to force this difference to this error on H, I forced A to 0, B to 1, and C to 1. That was strictly required. Now, the problem is that now, if I look at this value, I discover easily that this B and C forced to 1 will produce a 0 on F. And this will block the propagation of this error towards the output. Okay? Now, this means that in practice, the conditions for exciting the fault are not compatible with the conditions for propagating the fault. Here, the condition for propagating the fault through the end was that F was equal to 1. But F is equal to 0 if I apply the excitation conditions. So the two set of conditions cannot be combined, and this means that the fault cannot be tested, that there is no input vector able to detect this fault. Okay? For this reason, this fault is called untestable, is labeled as untestable. Okay, I cannot test it. Now, a few considerations about what this means. In practice, I cannot propagate the fault to any output. This means that in practice, the outputs of the circuit do not depend on the value on H. Okay? But if a line is not able to affect the values of the outputs, it means that the value on this line is not important. It doesn't matter. This line is redundant. And this is a general rule in the sense that when there is an untestable fault in a circuit, it means that typically there is some redundancy in the circuit. Now, a circuit with redundancy is a little bit special. I mean, it's a special case. Redundancy can be introduced by purpose, for example, to eliminate races, or it can be introduced due to bugs in the synthesis or to special situations in the design process. By sure, this will limit the achievable percentage of faults that can be detected, because untestable faults cannot be detected. So we will see in a moment that a very important parameter for test is the fault coverage, the percentage of faults for which I was able to generate a test vector over all the possible faults. Now, clearly, for untestable faults, it is impossible to generate such a test vector. So the fault coverage that I can achieve in the presence of untestable faults is lower. And this is the reason why untestable faults should be first identified and then observed to check whether I can do something depending on the reasons for the related redundancy. To summarize about the stacked fault model. Well, the stacked fault model has the characteristic of being able to model several physical defects that do behave exactly in the same manner as a stacked. Okay? It is relatively simple. I think it's easy to understand it, and it gives to a fault list which is composed of a reasonable and numerable number of faults. For all these reasons, it is well supported by EDA tools, CAD tools, and it is widely used. When I was saying that stacked faults may represent real defects, I was saying something true, and I want to show you an example. This is an OR gate at the transistor level, and let's imagine, let's say, a defect forcing transistor T1 to be permanently in conduction. This means that C is permanently connected to ground, and this means that the output will be always 0. Now, this defect can be easily modeled and suitably modeled as an A stacked 1. Obviously, this is not always true, in the sense that there are also physical defects that cannot be modeled resulting to any single stacked fault. This is a relatively more complex circuit implementing the Boolean function shown in the transparency. So f is 0 when either A or C are 1 and either B or D are 1. Okay, this is the function implemented by this circuit. Now, let's consider the case in which a defect breaks the connection between the two branches, lower branches of the circuit, as highlighted in transparency. Now, you can easily demonstrate, for example, by computing the function performed by the new faulty circuit, that this defect cannot be represented by any stacked fault. So there are defects that cannot be modeled using stacked faults. However, there is an interesting observation, experimental observation, stating the following. If you use the single stacked fault as the starting point and you generate test vectors able to detect all these single stacked faults, and then you apply these test vectors to real circuits, you will experience the fact that many defects will be detected. So no matter the fact that all the defects are really modeled by single stacked faults, it is true that the test vectors generated by targeting single stacked faults are very powerful. They are able to detect a huge percentage of defects. Not all, but a huge percentage. And this is another reason why the stacked fault model is so popular in practice. Until now, we spoke about combinational circuits. Given a stacked fault in a combinational circuit, either the fault is untestable, no test vector exists, or I can find at least one test vector able to detect it. Okay? Now, an important observation is the following. A single test vector may detect more than one stacked fault. So, for example, this input vector, 1100, is able to detect quite a number of stacked faults inside. In particular, you can try yourself, and you will discover that these 5 stacked faults are all detected by this single test vector. Okay? This is an important observation because we can use it to reduce the number of test vectors required to test all or most the stacked faults existing in a circuit. Now we can move the test generation process. Just understanding how the concepts we just introduced can be used and are used in practice in order to generate a test vector for a given circuit. In particular, we will see in a moment that given a stacked fault in a combinational circuit, there are algorithms and tools that can generate one test vector for this stacked fault, for detecting this stacked fault. Now, the general problem, however, is not simply to scan the list of possible stacked faults and for each one of them to generate a test vector, so that if there are m faults, stacked faults, we have m test vectors. Why? Because this is a waste of time, because every vector, as we just saw, is able to detect typically more than one stacked fault. And what we want is to minimize the number of test vectors we need to use, because in this way we can reduce the cost for testing. Reducing the duration of the test means reducing the cost for test. Why? Because of the high cost of the ATEs, the test equipment. Now, if a test equipment is so expensive, it will cost for buying it, but it will also cost for maintaining it. And the higher the throughput of the test process, the lower the number of test equipment I will need to produce a given throughput in terms of test production and test, of integrated circuit manufacturing and test. So it is important, very important, to reduce the test time and to reduce the number of test vectors that I will use to test my stacked faults. The whole test process which is used for this purpose is shown here. Here I reported again the two test phases, the test generation before manufacturing and the test application after manufacturing. And we will enter into more details in a moment about this scheme. This transparency reports the typical flow which is used when generating the test vectors for a combinational circuit. In particular, there is a first phase, which is the fault management phase, in which the gate level netlist of the circuit is considered, and out of it the list of single stacked fault is generated. Once this list of faults is available, we can enter a loop in which we consider, let's say, one fault at a time. Now, clearly the goal is to generate a set of test vectors able to detect all or most of the faults in the list. This loop starts by, or the internal part of this loop, the body of this loop, is composed of three parts, three steps. The first step corresponds to selecting one still untested faults. At the beginning, all faults are untested. I will select one fault, and then I will pass it to the second step, in which some software procedure will generate a test vector able to detect this fault. Now, this test vector may be able to detect further faults, as we saw. For this purpose, I will activate a fault simulation step in which all the faults which are also detected by the same test vector TV are marked as detected, okay, or tested. Then the loop will repeat, selecting another untested fault, generating another test vector able to detect it, and then fault simulating the test vector in order to identify other faults that may be detected by the same test vector. And the loop will continue until still undetected, untested faults exist in the fault list. Okay, this is the scheme which is implemented in, let's say, the commercial tools. Okay. Now, this scheme implements what is called automatic test pattern generation. So we are speaking about tools, software tools, because given the size and the complexity of today's circuit, it is clearly unfeasible to generate these test vectors by hand. Everything is automated, and there are these tools known as ATPG, or automatic test pattern generator or generation tools, working on gate level netlist, solving the problem. This is the architecture. Everything starts from the gate level circuit description. There is the fault manager generating the fault list, and there is this test pattern generator composed of a true test pattern generation targeting a single fault and generating a vector, and a fault simulation module. And the whole and the test pattern generator module implements the flow we discussed in the previous transparency. The final result will be the set of the test vectors covering all or most of the circuits, plus some report. As I said, the fault manager is able to generate the fault list. In some cases, it may also identify some of the untestable faults, but untestable fault identification in the general case is not trivial. while the test pattern generation is composed of a test pattern generation module and a fault simulation module. Here I'd like to clearly introduce a very important metric, which is the fault coverage. The fault coverage is the ratio between the number of detected faults at the end of the process and the total number of faults. Fault dropping is an easy concept to understand at this point, I hope, and it is the usage of the fault simulation to identify those faults that are also detected by a test vector generated targeting a given fault. Using fault dropping, I can reduce the number of iterations of the loop I was mentioning before, which means reducing the number of calls to the module generating a test vector for a given stacked fault. And clearly, the main cost from a computational point of view of the flow we saw is in the test pattern generation rather than in the fault simulation. Okay, so using a fault dropping and inserted in the previous flow, we can reduce the number of calls to the test pattern generation module and reduce the number of test vectors which are generated at the end of the process. Okay. Now, at the end of the ATPG process, commercial tools typically label faults in 3 categories. Well, clearly there is the most important category, which is the one of faults which have been tested, for which at least one test vector has been generated, tested. Then there is another category. Very often it is relatively small, but it depends on the circuit, which is the one of untestable faults. Faults that can be proven by the ATPG to be untestable. There are techniques for identifying these faults. The ATPG in general, in terms of algorithm, is able to either generate a test vector for a fault or to prove that the fault is untestable. Okay? Unfortunately, there is a third category, which is the one of aborted faults. So faults for which the ATPG is neither able to generate a test vector nor to prove that the fault is untestable. So the ATPG algorithms are typically based on a backtrack procedure, and in some, let's say, limit cases, worst cases, this backtrack procedure may run for very long periods. So it is common to introduce a threshold saying after a given number of backtracks, please stop. At this point, if the fault was not labeled as untestable, and since no test vector has been generated, the fault is labeled as aborted. Okay? For an aborted fault, what I can say is simply, I don't know. I'm not able to test it. It may be untestable, but I'm not sure about that. Okay? Clearly, the number of aborted faults is a good metric for judging the quality of an ATPG system. The lower, the higher the quality. Today, very commonly, ATPG commercial tools are able to limit to a very small number the number of aborted faults, saying that they are very high quality tools. Today we are simply saying that commercial tools exist able to generate test vectors for stacked faults in combinational circuits. Now, this is the result of big research efforts who started in the 60s and ended up in the 80s with the work by Hideo Fujiwara, who introduced in 84 the FAN algorithm, which is the basics for today's commercial tools. And all EDA suites by the major EDA vendors include today very efficient ATPG tools for managing combinational circuits. Clearly, an important observation is that real circuits typically are not combinational circuits, are sequential ones, and large sequential circuits. Now, for a sequential circuit, always focusing on stacked faults, what is able to detect a fault is not anymore a single test vector, but a sequence of input vectors. Let's see a simple example. Let's imagine, let's consider this very simple circuit composed of a single flip-flop. Okay. Now, if I will consider the stacked one fault on the output of the flip-flop, and assuming that the flip-flop cannot be forced in a, let's say, simple manner, acting on a reset, for example, to a known state, what I need is typically two clock cycles here, one for forcing a 0 on the input of the flip-flop. Then I will activate the clock. The flip-flop will sample this value, will store it inside, and will force the corresponding 0 on the output. This will excite the fault. And in the following clock cycle, I will force E to 1 in order to propagate the fault effect to the output F. So we need two test vectors, a test sequence composed of two clock cycles in order to detect my vector, my fault, excuse me. Now, this is a very simple circuit, a very simple sequential circuit, and the typical, the most important characteristic of it is that there is no loop. But the real sequential circuits do follow the Huffman model, which is reported here. And what happens is clearly that any combination, any stacked fault in the combinational logic, in order to be tested, we require some specific values on the primary inputs, but in general also on the pseudo primary inputs. Okay, because the excitation conditions and the propagation conditions for testing any fault inside the combinational circuit, the logic, will require specific values on the inputs of the combinational logic. But in order to force such values on the inputs of the combinational logic, I need to force the circuit to a state where the flip-flops hold the required value. And this may not be trivial, because forcing a sequential circuit to a given state may be tricky, and it is extremely computationally intensive to understand which is the sequence of input values able to force the circuit to such a state. But this state is required in order to excite the fault. Obviously, once the fault has been excited, the fault effects may propagate either to the primary outputs, fantastic, I will be able to detect the fault, or the pseudo-primary outputs, but the pseudo-primary outputs are not visible from the outside. In that case, it means that the fault, once excited, created an error in one or more flip-flops. But what I need is to make this error, this difference created by the fault, visible on the primary outputs. And this again leads to the necessity of identify an input sequence able to make the difference existing in at least one flip-flop visible on the primary output. This is to say that generating test sequences for sequential circuits is much more complex. Let's see a simple example just to have the feeling of how complex this procedure is. Now, here we will consider this simple circuit composed of two flip-flops, one primary inputs and one primary output. Okay, the two flip-flops have the direct output and the negated output. And let's consider the fault A stacked at 0. Let's assume that the two flip-flops are equipped with a reset signal. So by acting on the reset signal, I can force both of them to 0, which means that I can force easily Q2 to the value 1. Q2 is the Q2 negated is the negated value of the output of FF2. Okay, in this way I can excite the fault, and this is extremely easy. Now, once the fault is excited, I need to propagate it to the output O, because this is the only visible point in my circuit. In order to do so, I will try to propagate the error as much as possible, but the only thing I can do in one clock cycle is to propagate the error up to the input of the flip-flop number 2. And this is done by forcing I to 0, so that the AND and luckily also the OR become transparent and do propagate the fault effect. At the end of this time frame, flip-flop 2 will store a different value in the good circuit, 1, and in the faulty circuit, 0. Then I will activate the clock and a new time frame will start. In this new time frame, I will try to propagate the error existing in FF2 further, and what I can do here is to propagate this error up to the input of FF1 by forcing I to 1, because I to 1 will open the path passing through this AND gate and this OR gate. At the end of this time frame, the error produced by my fault will be stored, will be latched into the flip-flop number 1. Okay? Finally, I will activate the clock and a new time frame will start. In this time frame, I will try to propagate the fault affecting already Q1 and Q1 negated to the output. This is easy because I can easily control I to 1 so that the final AND can propagate the fault. Okay? In this way, the fault will reach the output and can be made visible. Okay? Now, to summarize, this means that a valid test sequence for the fault A stack at 0 corresponds to the three input vectors 0, 1, 1 applied to the single input of my circuit in 3 consecutive time frames, starting from the reset state, because I assumed that the 2 flip-flops can be forced to the 0, 0 state by just acting on a reset signal which is not shown in the picture. But I hope this example show to you the complexity, even on a small circuit, sequential circuit, in generating a valid test sequence for a stacked fault. Now, the real situation is that despite the big research efforts, especially in the 80s and in the 90s, the problem of devising an algorithm that could be used systematically to generate test sequences for stacked faults in sequential circuits was, let's say, unsuccessful. Okay, so still at the moment we don't have any real algorithm which is able for real circuit, real size circuits, sequential circuits, to generate test sequences. Now this is a problem because our circuits are sequential circuits. How this problem was solved? By circumventing it. Starting from the 80s, big companies, the first one was IBM, decided to introduce what was called design for testability. And the idea is relatively straightforward. Since we cannot test sequential circuits, we should introduce a test mode different than the normal mode, so that when we enter the test mode, we will force our circuit to become a combinational one from a test point of view. And in this way, we can test it because we know how to test a combinational circuit. Okay? This technique, which is called scan, we will comment it and introduce it in a moment, is the first design for testability technique that to be introduced. It is very popular, together with the other design for testability technique, which is called the BIST, the built-in cell test. And I think it is worth commenting it a little bit. So let's move to the fourth point in the agenda for today, in which I will introduce to you some key concepts about design for testability, scanning in general, in particular, and I will say a few words about in-field test. Design for testability. The motivations were introduced just a moment ago. In this case, the main motivation was we are not able to generate test sequences for the generic sequential circuit affected by a stacked fault. So we need to modify the circuit so that we can test it. Design for testability. Okay? And the key ideas are, first, the circuit can work in two different modes, normal and test. And typically there is an input signal that I can act on, moving the circuit to one or the other mode. When the circuit is moved to test mode, it is able to reconfigure itself so that I can test it like I would do for a combinational circuit. Okay? And this technique is called scan. Let's see how it works. So this is the usual architecture for a generic sequential circuit with the combinational logic, the flip-flops, the primary and pseudo-primary inputs, primary and pseudo-primary outputs. Now let's imagine what happens when there is a stacked fault inside the combinational logic. Okay? If there is a stacked fault there, what I will need is to force some input values on the primary inputs, but also on the pseudo-primary inputs. Okay? Those that an ATPG may generate for me when targeting this stacked fault. It is easy to force these values on the primary inputs. It's not easy at all to force these values on the pseudo-primary inputs because this would require moving the circuit to a given state. And this is tricky in a large circuit. Now, when these values are applied here, the effects of the fault may propagate to the primary outputs. Fantastic. In this case, I can detect the circuit immediately. But in the general case, they may also or only propagate to the pseudo-primary outputs. So let's imagine this second case, which is less optimistic but more realistic. The fault effects are only propagated to the pseudo-primary outputs. I cannot see them because the pseudo-primary outputs are not visible. So what I need, in principle, would be to latch this difference here in the flip-flops and then to propagate it, forcing the circuit to evolve in such a way that this difference will affect sooner or later the primary outputs. But this, again, will be very difficult from an algorithmic point of view, meaning that generating this input sequence that is able to make the values in the flip-flops visible on the primary outputs is hard. So the alternative solution implemented by scan is based on a few ideas. The first idea is to substitute in my circuit every flip-flop into a scan flip-flop. A scan flip-flop is a flip-flop, let's assume it is a D flip-flop, to which I added a max in front of the data input. Okay? You see here the max which I added. Okay? This max is controlled by a scan-enabled signal, which is practically the normal/test signal which is used to tell the circuit whether it should work in normal mode or in test mode. When in normal mode, the max connects directly the external D to the data input of the flip-flop, and the circuit works as usual. If the scan enable has the opposite value, meaning that we want to enter the test mode, the data input of the flip-flop is connected to this serial data input SDI. Okay? This is the first change. So all flip-flops are transformed into scan flip-flops, having these two additional input signals, the max in front of the data input, and an additional output signals, which is the serial data output, which is simply a copy of the data output queue. Second step, all flip-flops once transformed into scan flip-flops, are connected to form a chain. Now, what does this mean? It means that we will connect all the flip-flops, once transformed into scan flip-flops, in such a way that the SDO signal of one flip-flop is connected to the SDI signal of the following flip-flop in the chain. So all the flip-flops will form a sort of shift register, and the first flip-flop in the chain will be connected, the SDI signal of the first flip-flop in the chain will be connected to an additional input signal, which will be called scan-in, while the SDO signal of the last flip-flop in the chain will be connected to an additional output signal of the circuit, which will be called scan-out. Okay? So this means that we will transform the circuit, the flip-flop into scan flip-flop, connect them into a chain, and then add 3 further pins to my circuit: a scan-in, a scan-out, plus the normal test signal, which will be connected to the scan enable of all flip-flops. Okay? These are the transformations to be done on the hardware of the circuit in order to implement scan. How can we benefit of these transformations? Let's see how scan works. This is our circuit. Okay? The problem is that for testing a stackette in the combinational logic, we cannot control the pseudo-primary inputs and we cannot observe the pseudo-primary outputs. But now the flip-flops are scan flip-flops, and there is this scan-in and scan-out additional signals that can be used. So what we will do is, let's imagine that here we have we are considering a stackette fault in the combinational logic. Okay, so what I can imagine is that I could extract the combinational logic and give it feeding an ATPG process. And this ATPG process will tell me, in order to test a specific fault, stackette fault, you will need a given set of values on the primary inputs and on the pseudo-primary inputs. How can I force them into the flip-flops? And this is the first phase. The first phase will mean moving the circuit to test mode. Now the flip-flops do form a shift register, and acting on a scan-in and on the clock, I will shift in the bits corresponding to the values I want on the pseudo-primary inputs in order to test my fault into the flip-flops. At the end of this phase, the flip-flops will hold the values required to test my fault. And these values will feed the pseudo-primary inputs of my combinational logic. I will be easily able to control the primary inputs, so the test vector can be applied to the combinational logic. This test vector is known to be able to test some faults because it may have been generated by an ATPG. At the end of this point, so the combinational logic is stimulated by the values I wished, okay, detecting one or more faults. At this point, the combinational logic will produce some values that may produce some observable differences created by the fault on the primary output. In that case, the fault is detected full stop. Or in the more general case, these differences created by the fault will be visible on the pseudo-primary outputs only. But what I can do is now to move back the circuit to normal mode. In normal mode, the flip-flops do sample the values coming from the combinational logic. And so I can capture in the flip-flops the values on the pseudo-primary outputs, including the differences created by the fault or the faults I want to detect. At this point, I can state that the fault effects are visible in the flip-flops. Unfortunately, the flip-flops are not visible from the outside. But this is where scan plays a role again, because I will move back the circuit to test mode, And then I will shift out the values in the flip-flops, making them visible on scan out. And so if the circuit produced, if the fault produced any difference on the pseudo primary output, I can detect it because on the scan out I will be able to see these values. Okay, this is the simple way scan works, allowing to easily test all faults, stacked faults, in the combinational logic. Now, clearly this means, obviously, that in order to apply a given test vector, I need to move the circuit to test mode, shift in this test vector in the flip-flops, apply the specific values to the combinational logic, then capture the values in the flip-flops and shift them out. It's a relatively long procedure for every test vector, but it is effective and it can be easily automated. And these two things, effectiveness and automation, let's say, convinced all companies to use scan. Scan is systematically adopted in practice everywhere. Now, let me add a few important concepts before finishing. The first one is the concept of test escapes. Until now, I told you how to generate test vectors for combinational circuits, how to extend the test to sequential circuits using design for testability, in particular scan. Everything seems solved, but it is not. It is not because it is not always the case that the fault model we choose, for example, the stacked fault, is suitable enough to manage all possible defects. More complex fault models may require to be adopted because for cost purposes, for economical purposes, perhaps I decide not to achieve 100% full coverage because the test would be too long and the test cost too high. So for a given number of reasons, it is possible that a very, let's say, dangerous situation arises in which a faulty circuit is labeled as good. This situation is called a test escape. Once again, a faulty circuit is labeled as good by the test process. Okay? Now, test escapes are critical because at the end they mean that the customer will receive a faulty circuit. It will mount it on the PCB, it will start using it, and sooner or later the fault will produce a failure. And the customer clearly may be affected by this failure, may complain, and the failure may create issues. Okay, so test escapes are critical. The percentage of test escapes, or the absolute number of test escapes, is called the defect level. So the defect level measures how many faulty circuits are labeled as good. Now, the value of the defect level depends basically on two factors. The first one is the test process. The better the test process, the lower the defect level. However, be careful because the value of the defect level also depends on the quality of the manufacturing process. If the manufacturing process is nearly perfect, it produces very few faulty products, even a medium quality test process may produce a relatively low defect level. On the other side, if the manufacturing process is extremely, let's say, immature, meaning that a lot of faulty products are manufactured, well, the test process should be very selective, very high quality in order to guarantee that only a limited, let's say, value of the defect level is produced. Just to give you an idea, the defect level is typically measured in parts per million, meaning that just a few circuits out of 1 million produced and tested are labeled as good, being faulty. In some domains, we always also speak about the parts per billion, okay, to give you the clear idea of how low the defect level should be. Okay. Clearly, if I want to achieve a sufficiently low defect level, well, it will be a long path. It requires using the suitable fault models, really able to represent the real defects. It means using solutions to exactly observe very well these fault models, generating test vectors, and applying these test vectors, take into account that economics are important. So the cost for the test is also important, the time to market is also important, etc. Okay? And devising the best trade-off between all these constraints is the task of the test engineer in cooperation with the different players in the company. A few words about in-field test. At the very beginning of the talk, I told you that we focused a lot on manufacturing, end of manufacturing test, but especially with the new technologies, it is important also to perform in-field test. Why? Because today it is important to be able to detect also faults arising during the operational phase. So imagine the manufacturing process may introduce some defects. End of manufacturing is expected to detect them. So circuits having some defect introduced by the manufacturing process are expected to be removed by the end of manufacturing test. Then the circuits are mounted on the PCB, and during the PCB assembly process, some defects may be introduced either in the circuits or on the PCB. A step called PCB test is performed to remove boards which are faulty. Then, even if the board is perfectly fault-free, it is mounted on the system, and everything works perfectly at the beginning of the operational phase, it may be that during the operational phase, some defect arise. Okay? Why? For example, due to aging. New semiconductor technology are more prone to aging than the old and more mature ones. So we need to perform periodically some in-field test in order to detect these faults that have been that arose or are arising in the circuit during the operational phase. Now, the importance of in-field test comes from two factors. The first one is that, as I was saying, the most advanced semiconductor technologies are more prone to aging and to faults arising during the operational phase. On the other side, ICs are used more and more in safety critical applications, like healthcare, space, automotive, robotics, etc., where we cannot accept that failures may arise. Failures may arise, but with a very, very low probability. Otherwise, the product cannot be deployed and used. This means that I need to implement in-field test. In-field test aims at detecting the occurrence of faults as soon as possible, so that typically I can warn the user that a fault arose before it produced a failure, or I can even reconfigure the system so that the fault is masked, or I can, let's say, put the system out of service, and in this case, perhaps a spare system exists so that the system operation can continue. The issue is that in-field test has some peculiar characteristics. First of all, we want to test the circuit while it is in the system, on the board, etc. So I cannot resort to a tester where I place the circuit, I apply stimuli, and I observe the answers. Okay, this cannot be done. So the only solution is that the circuit can test itself. So from the outside, I will ask the circuit to test itself, and the circuit should be able to do so for in-field test. Second point, in-field test is done either at the power on, in this case, the application is not running yet, and I have some freedom. But very often it is done during the operational phase while the application is running. For example, exploiting the idle times of the application. So the application stops for a short period, and during this short period, I will launch the test. then the application will resume. So I need to interfere in a minimal manner with the application. I cannot disrupt the content of the flip-flops or of the memory. Okay, and the duration should fit the idle period I can use. So there is an issue of low intrusiveness of the test. And finally, there is an issue which is not only technical. The infield test should be able to detect faults, but the company knowing which are the faults arising in a circuit is the semiconductor company. But the infield test is typically deployed by the system company knowing the application. For example, knowing when the test should be launched, which are the constraints for the infield test. So the result is that the infield test will only be effective if the two companies will work together. And when two companies work together, there are issues of confidentiality. This is a further issue that make infield test more complex to manage in several cases. Okay, but there are obviously solutions for that. Conclusions for my talk. Well, I hope I convinced you that test of an integrated circuit is a crucial step, both at the end of the manufacturing process and during the product operational life. For implementing test, we resort to fault models, and we use the stacked fault model as an example. I introduced to you the key idea of design for testability, which is systematically used to allow the test of real circuits. Without design for testability, we would not be able to test the real circuits. And finally, I stress the fact that in order to achieve a sufficiently low defect level, we need to combine different techniques in a very smart and clever manner. Let me conclude with by mentioning some hot topics in an integrated circuit test domain. Because this domain, the area of test of integrated circuit, is a really hot research area requiring continuous adaptation and evolution of the known techniques. So yes, there are some solved problems, but there are many open problems. Matching the, let's say, evolution of the technology, both from the semiconductor point of view and from the application point of view. Just to mention a few, there is the issue of defining new fault models better addressing the new semiconductor technologies. There is the issue of devising new DFT solutions, reducing the test cost while still matching the quality requirements of several domains. And there is the big issue of devising new techniques for effective in-field test. All these problems and issues are hot topics. The test community gather in some important venues, and one of them is definitely the European Test Symposium. For this reason, if you want to be updated on the latest news in this domain, or you want to propose your ideas for solving these problems, the venue for doing that is definitely the European Test Symposium. This is the call for paper for the next edition. I urge you to consider the possibility of submitting scientific papers, but also proposal for tutorials, special sessions, panel sessions, etc. And I urge you to consider the possibility of attending the event in the very nice location of next year, Hania in Greece. The call for papers is already available on the website. Please consider the possibility. I hope to meet all of you there. Thank you for listening to me. If you have any question, you can refer to me, for example, via email, and I will be pleased to answer you. Have a good day.